Now, so we've been talking about rotating vectors and space vectors, we call them, and then how those vectors can be looked at from two axes. So we can convert them to two axes, and then we also just mentioned briefly how we can convert that to a rotating frame. So basically, this is a form of mathematics that we are going to go through to simplify our machine and the overall system analysis when it comes to AC machines. And this is known as reference frame transformation. Okay, reference frame transformation. And in a nutshell, it's like looking at your AC currents from a frame that is at the same frequency as the AC currents, which makes your machine, your currents, your voltages that are oscillating to look like stationary, like DC. Okay, so the types of frames of interest depend on the type of machines, because if you look at AC machines, induction machines later, we'll see that there are several different frequencies associated with an induction machine, which is an asynchronous machine, whereas synchronous machines, we can only associate a couple of different types of frames, synchronous frame and the stator frame. Of course, you can look at it from a different frame other than those, but it won't make your life any easier than the rotor reference frame. Okay, so we can also, with this method, with this transformation, we can transform variables such as inductance, currents, flux linkages, apart from voltages and currents. So that's going to be very helpful, and we'll learn about that. And even more, the reference frame transformation is not only for machine analysis, it's used for power systems, and then again also for control of AC machines. Okay, so when you design controllers, we're going to use this approach again to simplify our control systems. Now, so last time I think we basically went over this, but I want to refresh, review that before we proceed. We talked about three-phase variables, and then we said, these vectors are going to be changing, right? I'm using F so that I can represent any other variable like voltage, current, flux linkage. So it captures any type of such signal. Now they vary with time, right? The amplitude changes, and a combination of them along with the spatial distribution gives us a rotating vector, right? We talked about this rotating vector that goes around at the omega frequency. All right. Now what happens is, since you have a rotating vector at any instance in time, wherever it is at, we can always find the x-axis projection. So how much of it is projected on this axis, and then how much of it is projected on the y-axis. So the projections on the perpendicular axis. Now, standard form is, we say this is x, this is y, right? Now, so this is important in our analysis that we are going to go discuss. Our definitions of the two axes are going to be f alpha and f beta, and the positive directions are in these directions. Okay, and this is important when you go into reference frame analysis to early on establish this frame, this axis system, because all your math will rely on this. And the reason I am using this structure is because this is where most of the books have used it, and in general literature, this is how they refer to the system. So I'm going to continue with that frame, these axis naming conventions. But you are welcome to change, and then you'll have to adapt your math for such systems. All right. Now, I hope this is clear that we have this rotating vector, whether it's voltage, current, flux, and as it rotates, the projections on alpha and beta are going to change. They are going to look like sinusoids, right? So to begin with, initially, we had three sines, right? Sines or cosines, sinusoidally varying waveforms. Garrett, when you say have you been using this concept already, do you mean in another class,
I
maybe?
mean, like how we represent like AC signals using, like, I know this is like gain, but like using magnitude over frequency in like a Bodhi plot. So instead of having like a frequency response, you have the just the gain or just the amplitude.
This is a little bit different. I know what you are saying. You are saying, okay, if you are looking at from a frequency response perspective or a body plot, that is only specifying how the gain works, right? For across different frequencies, So in a body plot, that basically says, okay, at this frequency, right, you have this much of gain or this much of amplitude. So for a low pass, right, it's going to look something like that. But what we are going to look at in terms of reference frame transformation is we are going to go into a particular frame. For example, the observer being us or the controller being a certain control system, you will be on that frame itself. For example, it's like surfing and you are riding the wave, so you're going to be on that wave rather than sitting on the beach and seeing different waveforms, different frequencies of waves come and go. You're going to be on the wave. That way you are moving with the wave. Okay, so it's a little bit different from what all of you have seen for the most part. Okay, and so we had these three-phase sinusoids from the three-phase system. Now we have a convenient way of representing everything in this three-phase system just using two waveforms. Okay, now mathematically this is going to be a little bit confusing. Like we had three variables and now we are showing that with two variables. How is that possible? Well, technically speaking, we have another variable. That variable is actually going to be zero. So the zero sequence variable, we won't talk about it at this stage, but when we go to the final equation forms, you will see that we go from three sinusoidal variables to three variables that are two are sinusoidal. For a balanced system, your zero sequence is going to be zero. Okay, so just keep that in mind. Overall, the general concept, at least what we are trying to do, is that understood. So we are basically, for now, we converted from the three waveforms, we came up with two waveforms with respect to this new axis system. Okay, F alpha, F beta. We are looking at the components and that's what they look like, only the projections. Okay, all right. So that we called Clark transform. We talked about that. This a lady, Edith Clark, proposed that. There is a very nice paper on how this is being used for, I believe, synchronous machine analysis back in the days, maybe 1930s, if I remember right. And so from ABC frame, this is what we call the stationary frame, meaning everything or the observer is stationary. We are looking at the currents from a stationary frame. So we, that way, in that case, our speed is zero. We are not oscillating. Okay, so and we are transforming these A, B, C variables to alpha, beta, and this is that zero sequence I mentioned earlier. Okay, alpha, beta, and zero and then if you compute this for our three-phase balance system, this is going to be 0. Okay, you're welcome to compute that. Now, so this is Clark transform, and you can show it in matrix form. And also, if you want to transform from alpha beta 0 to back to ABC, you can even compute an inverse matrix for that. Okay, so that way you can, your FABC is going to be inverse of Clark transform times F alpha beta 0. Some people call it alpha beta gamma. Okay, so this is the Clark transform, and typically they call this the 3-to-2 variable in industry very loosely, but be careful, technically that third variable is there, but it's under an assumption which sometimes can get violated, and you need to be a little bit careful in that case. All right, so Clark transform, we spoke about this last time. Now the next one is very interesting. Okay, now stationary. So previously we said our axes alpha beta are stationary, they are staying in place, they're staying in place, and the vector is rotating, right? The vector is rotating, and now we are looking at the projections. Now in the Park transform, this was also developed back in the days in 1930s. What they came up with is, now why not look, why should we look at from a stationary frame? Why don't we move with the vector? Why don't we come up with an axis system that can move with the vector? Okay, and of course, in order for us to move the reference frame, we need to know how far the vector has rotated, whether voltage, whether it's current, whether it's the magnetic field, the rotor magnetic field. We need some mechanism to know how much it has rotated. Okay, and that is where the position sensor comes in. And there are sensored methods, there are sensorless methods of obtaining how much rotation did this vector rotate. For now, we'll treat it in a generic form as a rotating vector. Now, if you want to follow the vector, then we need to know the exact position it shifted by. Alternatively, you don't even need to follow that vector. Let's say your vector is rotating at an omega frequency. We want to transform all those variables, or at least the vector projections, to a frame that is rotating at omega 1. So maybe we are moving at a frequency twice that, or 3 times, 4 times, right? 5 times. For some reason, this is hypothetical, right? So we want to be able to transform, and then this transformation method lets us transform our variables in that way. All right, so we look at how to do that. So do you understand the difference between the stationary versus rotating frame now? So initially we had alpha beta, they are fixed, they are not rotating. Now in this new case, we have an axis system, we call them the Q and D, quadrature and direct, and I'll explain to you what that is. Quadrature and direct, those axes are moving with the vector. We are moving with the vector. You don't have to, you can go 1.5 times the vector, but the idea is this frame, this new frame is a rotating frame. Okay, you can move along with the vector, which gives us some benefits, and we'll talk about what those benefits are. All right, is that clear? What our goal is, at least? Okay, now since we have alpha beta here, it's a plane, right? You need two coordinates or two measurements to determine that vector, the full vector, without loss of information. And even in the new axis system, you still need two measurements. You need what we call the Q quadrature component, and then D the direct component. Okay, so you're going to still need two components here. So we call them two variables to two variables transformation. Again, there is this zero sequence. We are assuming that to be zero for now. Mathematically speaking, this is still a three variable to three variable transformation. All right. Now, this axis alignment is key. Axis alignment is key. The reason is, for example, let's say your vector is like this, right? And it's rotating, and you are moving at the same rate as the vector, but you have a certain offset. So let me try to redraw this in a different piece of paper. So let's say I have my normal axis system, all right? And then let me get my rotating vector. So my rotating vector, let's say the rotating vector is like this at t equals 0, all right? Rotating vector. And then my axis system, I am assigning the axis system at t equals 0 like this. Okay, so let's say we have a 45 degrees angle offset. Okay, so this is my Q, this is my D. All right, and either in a certain period of time, what will happen is the vector will rotate. All right, the vector will rotate. That means, let's say the vector moved 45, moved by 15 degrees, right? 45 plus 15, what do we get? 45, 55, 60, right? So it moved by 15 degrees. So what happened to our reference frame? Reference frame would have moved along with it, right? Because it's connected to the vector. It's moving at the same frequency. So let's make that assumption. These are 90 degrees out of phase still. It's still maintaining this 45 degrees angle because our reference frame is going at the same frequency as our vector frequency. Okay, now let's see if we get the value of this. Right now, let's say you are on this rotating frame, this green frame, all right, and you are looking at the projections of the vector on this Q and D orthogonal axes. Okay, you are looking at the projection, you are seeing, okay, I have this much here because it's 45, and I have this much negative because this is positive direction, right? So we'll call this one y, no, we call this x1, we'll call this y1. All right, now we come to after, this is t equals 0, this is t equals t1, different time instance. Okay, now from this new after the rotation, you are still on this new axis system, right? You're still on this. What do you think you will see as the projections of the vector at this time? Exactly, they are going to be the same. They are going to be the same, right? So you're going to see them as x1 and y1. Okay, so that is crucial. They didn't change. Okay, now if let's say we aligned our q axis with the vector to begin with, what can we say about the direct axis component? The projection on the direct axis. So if we started with, for example, if we say our vector started like this, we are saying, you know what, I'm gonna I'm not going to have an initial offset. I'm going to set my Q to this direction and D to this direction. And then I will move along with my vector at the same speed. What can I say about the projection of the vector on the direct axis? This is my vector. What is the projection of the vector on the direct axis? Well, 0, right? The amount of projection is 0, right? So as what will happen is, since you are moving along with it, you're going to see the full magnitude of the vector along q axis. Okay. All right. So now, so this is one scenario. This is the second scenario, and then we can think of a third scenario where the vector and the reference frame, they are going at two different velocities. Okay, so when they're going at two different velocities, what you'll see that depending on the relative speed difference, you will see either a faster or a slower sinusoid when you are looking at the vector from your frame of reference. Okay. Now, what will happen is that the importance here is when you are aligned and when you are rotating at the same velocity. For synchronous machines, this gives us an advantage because now you can observe your machine variables from this rotating frame, while, because all of your currents are go at a synchronous frequency, your voltages are at synchronous frequency. Therefore, you can look at your you will see your variables as DC. So if you are to plot the measurements, right? If you are to plot either case, if you are rotating at the same frequency at t equals 0 and t equals t1, you're going to see the same magnitude, right? If this is your q axis measurement or q projection amplitude, you're going to see the same value as long as you're going at the same frequency. If you slow down or go slightly faster, then you will see some sinusoid. But having this rotating frame helps us observe the system as a DC system or a steady system. So that is the advantage. And then depending on the relative axis alignment, you can decide if you will want to see a certain value on direct axis, or you only want to see full amplitude on q axis, or do you want to have a partition of the vector between q and d axis. Okay. Is that good? Is that
So the DC representation that we're looking at is just the projections.
just the projection? So in real life, in this, if you are looking at the stationary frame, which is, you know, someone standing here, someone sitting down, right? Someone sitting down here, they're still going to see this vector rotate, right? They're going to still see that vector rotate. Only for the person on this reference frame is going to see it as a DC. Is that understood? Is that clear? That's important, right? That's very important. Okay. So
That give.
say that again.
Why is that helpful then?
Exactly. So you're not going to see the value just yet. You will see the value when we go into synchronous machine analysis, because we can now convert our AC currents to look like DC currents using this transformation. And now your controller can treat your motor as a DC motor or a first order plant than an AC signal. Okay. Okay. So for now, we are just trying to understand the mathematics here, and then maybe a little bit of an idea of how this vector will project onto the different axes. When will that projections look sinusoidal? When will that projections look DC like? Okay, they're only looking like DC because you are operating at the same frequency. You are moving at the same frequency. Okay, so what we'll typically do is we typically attach our Q and D axis along with the vector, quadrature along with the currents that we apply, and direct is along with the magnetic flux of the rotor for a synchronous machine. Okay, direct means directly along with the magnetic flux. Quadrature means 90 degrees out of phase from that flux, rotor flux. All right. Now, in a machine, when you look at a machine, you're going to have how many fields in it? How many fields, how many magnetic fields need to interact to generate torque? Exactly. Yeah, you need two magnetic fields, right? You're going to have a rotor magnetic field and a stator magnetic field. Both are going to be rotating. All right. So now we need to be very careful when we specify where we are attaching our frames. Typically, we tend to bring all the variables to one frame. If we take the motor, the stator currents to rotor reference frame, we will take the motor parameters to rotor reference frame as well as our flux linkages, the permanent magnet flux, all that get transformed. Otherwise, it will not be very straightforward. It'll be like a mix of variables and it's not easy to understand. So we'll talk about that in detail. I lost my train of thoughts there. But oh yeah, I forget. Okay, but there are two fields, so you need to pay attention. What field are we talking about when we say Q and D? Okay, you'll hear this term quadrature and direct axis very often. So yeah, so alpha beta projections transform to QD. So what we'll do is we look at the alpha beta projections of the vector, and then what we do is we transform those projections, or we take those projections along with our rotating vector. Okay, so that is what we call Park transform. Park transform, and it's a very simple transform, a frame transform relationship. And theta is basically how much has the vector rotated, vector of interest. Maybe it's a voltage vector, maybe it's a current vector, maybe it's a flux vector, but how much has it rotated is important, and that's where the position sensors will come into discussion. Okay, so alpha beta, so we have the quadrature and direct axis relationship with alpha beta. Okay, so these two variables being converted to two variables here. Right. So in general, what we do is when we have such in this case, to make our life easier, we have a Clark and a Park transform. So instead of treating them separately, what we do is we combine them to a one transformation. You use a reference frame KS, at least that's what I'm used to learning with. You can call it any name you want. And then that combined transformation matrix is this matrix. Okay, and then FABCS, this is FAS, FBS, and FCS. This is a vector, right? That vector gets multiplied with KS, and which results in FQ, FD, and F0. F0. All right. Now, what is this theta now? For our transformation, what is that theta? That theta depends on what frame we want to transform our signals or system 2. Okay, if we want to transform it to a rotor reference frame, then we need to know the position of the rotor. Okay, we need to know the position of the rotor at every instant. At every instant. Come on. Sorry, my computer locked out. So we need to know now if you want to. So this theta is basically your speed. If you are assuming you are going, if you know the speed, right? Integral of speed with respect to time plus your initial or starting position. All right. So this is your theta. You can choose this frequency to be any frequency. It need not to be your rotor frequency or your stator frequency, or it can be arbitrary, because that way we study the math in a more generic sense. But now when we go into our machine analysis, we can apply it to the specific machine using the frequency of interest. For synchronous machines, typically we use the synchronous frequency to study the machine. Okay, but you can look at it from any frequency. You can look at it from a faster moving frequency, slowly moving frequency. But what will happen is if you're moving faster or slower, then you will still see some of the waveforms as sinusoids. So your math might be a little bit more complicated. Okay, so this is the combined Clark-Park transform. Of course, you can come up with an inverse transform for that, because if you want to convert any variable from the rotating frame or that arbitrary reference frame, which is moving at omega, to back into our stationary frame, right? So this is that inverse transform that you can use. All right. And if you want to try, I would recommend, just generate 3 sine waves in MATLAB, in Simulink, apply this transformation with the position, and you'll see that your measurements will look DC. They'll look like steady. And you can even play with your frequency. You can change it to slightly different, a lot more different, reverse. You'll see different phenomena happening when you change your frequency from that synchronous frequency. Now, in this method, we call this transformation, this KS matrix that we talked about earlier, a power invariant method. Power invariant method. What that does is, once you transform from ABC frame to DQ frame, the total power does not change. Okay, just because in the mathematically the power does not change. Of course, you can come up with transformations that the power does change, but for applications that we are going to look at, we prefer a power invariant transform, because we are looking at machines and how much energy, how much power it's going to consume, right? So we are looking at a power invariant method, and that 3/2 in our transformation is from that power invariant. This 2/3 is for that power invariance approach. If you look at different literature, they might be using voltage invariance. Just be cautious of that. Okay. So we know the forward transform, we know the inverse transform. So what can we do next, right? So next, what we can do is we can actually try to even apply them to variables. We can transform variables such as resistive elements. Okay, resistive elements. We are looking at this very simple relationship. We have VAS, VBS, VCS, and then we have 3 resistive circuits. So if you want to visualize that, it would be something like this. Right? So you have a three-phase system, can be a delta. We have our VAS. This is our VAS applied. This is, VBS. This is VCS. And then you have your currents flowing, right? And these are resistive elements. Resistive elements. Okay. And then this is the simple representation we can come up with for this system. Okay. Now, in order to transform these to our rotor reference frame, pay attention. If you look at our relationship, let me go back to the previous page. So ABCS, FABCS, F being any variable voltage or current, times KS gets me to the arbitrary reference frame, okay, or QD frame, if you want to call it. So I'm going to left multiply with KS matrix here. Since I left multiplied my left hand side, I want to left multiply my right hand side. Okay, I multiplied my right hand side. Now I have IABCS that I want to convert to QD, or the arbitrary frame, right? So if you have our ABC frame, the stationary frame values, then if I can write this equation again as the following. ABCS is equal to KS inverse times QD0, right? You can say that. It's just left to multiply with an inverse. So instead of IABCS, I can write KS inverse times IQD0, right? So that's what I'm going to write here, IQD0S. Now, all my voltages and currents are in this arbitrary reference frame, QD0 frame, right? And so if you solve for this KS times RS KS inverse, that is what your resistors will look like in this new rotating frame. All right, but guess what? For resistors like this, equal and balance in this configuration, when you do this transformation, you still get this RS matrix. So I'll use this symbol, RS matrix. Okay, so despite the transformation, the resistive circuit, if they are the same, it will remain in the same configuration. Okay, their values will be the same. You'll have a Q, you'll have a D, and you have a 0. You'll have the same three values. However, if they are different, if they're not the same value, now that's a different scenario. Okay, I encourage you to try change the values, change the diagonal values a little bit. You can even plug in numerical values and try to transform and see what you get. You can use MATLAB symbolic toolbox. You can add off diagonal elements, see what that does, because there might be some systems that you come up with in circuits. I can't think of an example for resistors at least right now. But if they are equal, if they are on the diagonal, which is what we assume for machines, you get the same RS value. Okay, so for resistive elements, this works fine. It looks okay, right? Let's see what happens next. Now, we're going to look at inductive elements. Inductive elements is again valid for flux linkages. So first of all, we look at flux linkages here. Are you guys with me? Are you guys with me? Okay, good. All right. So flux linkages, and so basically rate of change of flux linkage is a voltage, right? This is like back EMF. So and we know lambda is Li. Li, remember, this is from our 441 discussion. So what we're going to do is we're going to try to transform all this into our arbitrary reference frame. Again, we're going to follow the same procedure, right? Left multiply with ks, and then inside lambda abcs, we change this to ks inverse lambda qd0s. Now, the p I'm referring to here is d over dt. It's the derivative operator. I'm going to use that as a variable. This is a standard practice. I'm not sure if all of you have seen this in the past, but we can mathematically notation wise, we can use this approach, especially to show that what happens is, since ks is theta dependent, now we have to consider the derivative, including, treating this as a product, right? Because your theta is also going to be varying with time. So when you do that, what you have is this relationship. So you can break it into two, right? You can break the one derivative term into two. So ks is still there. We're going to consider the derivative of the lambda qd0s separately, and then we're going to consider the combined or the combination of the two, or just the ks inverse. All right. So now when you look at ks inverse, let me show you what we have inside that matrix. We have theta, right? So now when you take the rate of change of this whole matrix, first of all, we have to take the derivative of the matrix with respect to theta. And then we have to look at d theta over dt separately. What is the rate of change of position, or rate of change of angular position? We have a name for it, right? What is that? That is, yeah, angular velocity, exactly. So that is what we get as the common variable times the elements, the derivative of the variables inside the matrix. Okay, so the derivative of ks inverse ends up being this matrix. Okay, so what now we can do is we can take that relationship and substitute back into our equation. And when you do that, what you get is you get ks times pks inverse equal to this matrix. Let me quickly flip back here. So therefore, this becomes all that times lambda qd0s, and then ks times ks inverse is basically 1. Therefore, we are left with this relationship. Okay, so omega times lambda dq, see that swap of the variable qd to dq, because of this product, it actually swapped the variables that goes into the q axis. Okay, so here this remains the same. So this is our vqs, vds, v0s, and we can clearly see that there is some cross coupling. See, vq variables are in the d axis, some d variables are in the q axis. Okay, so this is called cross coupling. You will see this in synchronous machines when we go to analyze them. All right, and then since this is a speed, we have a speed factor associated with it, and it's resulting in a voltage. We call it a speed voltage. Okay, speed voltage in our equation. But so this is what happens to flux linkage, or at least rate of change of flux linkages. If you have linear inductance values, like that, where you can represent them as a combination of inductance and current, now we can actually easily treat them as, if they are balanced, if they are equal, that is like, if they are like this, then you have the same element in the diagonal and they transform into the same matrix. Ks ls ks inverse becomes the same matrix. Okay, so this is a convenient solution for us. However, when it comes to true machines, what happens is there is cross coupling. cross-coupling, okay, which means your magnetic fields not only couples to yourself or itself, but it couples to other windings, other phases, which is captured through this mutual flux. Remember when we talked about transformers, the transformers that transform voltage, not that transform into vehicles. We talked about self-inductance and mutual inductance. Okay, how much of flux is linking through this because of this current in this winding, right? We talked about the mutual inductance component there. So the same principle applies when it comes to an AC machine, because you're going to have current flowing through A winding, and that flux is going to link through, at least portion of that is going to link through B winding, right? So, so if this is B prime, it's going to link through, and that creates the cross coupling. And then if you have such an ideal machine that's symmetric with cross coupling, your matrix is going to look like this: equal amount of cross coupling or mutual inductance. Okay, LLS is leakage inductance. You guys know that too. Leakage, remember? Leakage inductance, right? Transformer, same principle applies. You can have some leakage here, and also at the end of the motor where the winding bends, you're going to see some leakage. Okay, you have some leakage inductance, and then you have your mutual inductance in your inductance matrix. So a symmetric coupled network. This is a practical three-phase winding set. Okay, and when you transform such a system, you're going to get a relationship as this. So if it's symmetric and coupled, you're going to get all diagonal elements where we see key primary inductances on those two elements on the Q and D. Zero sequence is primarily based on leakage, and the off diagonal elements go to zero after the transformation. Okay, so the important is, see, magnetically decoupled. When you do the transformation initially in the stator frame, it was magnetically coupled. Now when you go into this arbitrary frame, you are able to decouple those inductances, magnetically speaking. Okay, so this is an advantage that you're going to have when we go and analyze machines. Okay, what else? Again, this is for symmetric and coupled, but practically speaking, if you measure an inductance, if you have done that in real life, you'll see that, you know, these are going to be slightly different from each other. They're not going to be the same. These are not going to be the same either. Okay, and when that happens, you're going to see some off diagonal components appear. So it becomes a little bit tricky when you do analysis. Typically, we assume there are no such non-idealities, at least for controls, at least for basic analysis. If you are a motor designer, then you might be concerned about how you want to approach those, how much of imbalance is there, things like that will be of concern to you. Okay, so so we talked about quite a bit here, starting from our transformation. So let's go back, you know, just a little bit of a review before wrap up for today. Okay, so we basically looked at our Clark and Park transformations, and then we said we can combine the two into one matrix here, right? And then we said, okay, we call this the power invariant method, and then we said we can use that transformation and convert resistive elements. You can convert voltages, inductances, and what else? Linear magnetic circuits, and transform those variables into this arbitrary reference frame. Okay, okay, arbitrary reference frame. Now what I want you guys to do is go through this carefully. I don't know if you have taken any notes or anything, but once I post it, you can go back and review this, go through this, because what we'll do next time, we'll do an example on how can we apply this to a little bit more realistic application. Okay, not a full-fledged machine, but somewhat of a combination of inductance and resistors, and let's see what that results in, because that will help us understand the deeper concepts when we go into machines. Okay, because the machine has resistors, inductance, mutual inductance, back EMF, all in one equation. So if we want to understand that, we want to have that initial basic knowledge behind how to use this transformation for analysis. Okay, and it's very nice. I'd say, out of the things I have learned, this is very interesting. This is very beautiful in terms of mathematics, and there is a lot to learn, lot to study in these systems, and I still learn new things even just by analyzing them in a deeper fashion through electric drives. Okay, all right, so any questions? I'm gonna end this for now. Let me find